Examples of problems, 11 and 12, are mass mole problems, where we're starting with a specific mass of substance. Say we got 10 grams of potassium chlorate. We'd be starting here in the mole tunnel, for those of you that like that, or here in the train tracks, for those of you that like the train track method. We would divide by the molar mass of the compound or substance in question, and then do a mole ratio. We'd be stopping right here in this kind of problem. So it's divide by molar mass, do the mole ratio, boom, done. Make sure on this test that you read carefully to see what unit is being asked for, what quantity. If it's mass all the way to mass in grams, then boom, go through the whole process, all the steps. If it's just a mole problem, you're going from here to here, just a proportion. And then you're either starting with mass and ending at moles of the other substance, or you're starting at moles of one and going all the way to mass of the other substance. And on that kind of problem, we do the ratio step and then multiply by the molar mass of the new substance that we're trying to find. Okay? These questions are not going to be too tricky. I'm only highlighting the basic procedures here and referencing our format so you have something to practice from. That takes us to test hint 13 and 14, which is a mass-mass problem. Again, balanced equations are going to be provided for you. I bet on the honors page, though, the balanced equation is not going to be there. Yeah, that would be a good thing to make it an honors page question instead of just a regular test question. So you might have a word problem and a description of a chemical reaction. You may even have to do some reaction prediction, where you know the type of reaction and you figure out what the products are going to be. You write all the correct chemical formulas for everything. Then you balance your equation by counting the number of atoms left and right. This should sound a lot like the last two chapters we've done. And then you throw the recipe on top of that. So starting with a given amount of one substance, finding a specific amount of another substance. But back to this test, the two questions here have the balanced equation already provided. You will be given a particular mass of a substance to start with, and you may or may not have what we call a limiting reactant. You might have to check that. Okay? So that means you're just starting the mole tunnel twice. You're given a mass of two different substances. You're going to divide each by its own molar mass. See how many moles of each you have. If it happens to be in the same proportion as the balanced equation, you're good to go. You don't have a limiting reactant. But if it's not in the same proportion as the balanced equation, then you don't have enough of one of those. We saw that in our iron and copper sulfate lab way back a long time ago. I think at the very beginning of this chapter, and even the beginning of the reactions chapter, where we put in a specific amount of iron filings and then a whole bunch of copper sulfate that we dissolved to make an aqueous solution. We ended up having excess copper sulfate. We knew from our balanced equation and the amount of iron filings we put in that we need a specific number of moles, and it had to match the ratio in the balanced equation. And then we didn't worry about the excess copper sulfate. We only used up a certain amount of it. We had plenty left over. It didn't take part in the reaction. So when you're given data in a particular problem, you're going to have to see how many moles of each substance are given, match that back to the balanced equation. And 9 times out of 10 in this kind of problem, because I'm testing you on limiting reactants, it won't be in the same ratio as the balanced equation. You'll have to identify which one you don't have enough of, and that's strictly based on the mole ratio. So you're at this comparison step, no big deal. And then you complete your mole tunnel problem, if we're going with this method, based on the limiting reactant. The excess reactant, we abandon the tunnel. We stop digging it, and we just ignore it, and we keep going from the one that is the limiting reactant. The limiting reactant always determines the amount of product we get out, or the amount of other substance we need. Number 15, test hint number 15. How to calculate percent yield for a given reaction. We have a couple of these. All right. If you do a mole tunnel problem or train track method, either way is fine, what you are calculating is the theoretical yield. We put in 5 grams of potassium chlorate. We divide by its molar mass to get moles. We look at a mole ratio, say, between potassium chlorate and oxygen. It's a 2 to 3 ratio, so we're multiplying by 3 divided by 2. We multiply by the molar mass of oxygen to see how much oxygen we could get out if we put in 5 grams of potassium chlorate. That's if we got 100%. If we accounted for all the atoms, that's our theoretical yield, 100%. And you saw in the lead iodide lab with that glorious yellow precipitate that there are a lot of places where atoms can be lost when we're actually conducting a laboratory experiment. There was lead iodide residue on stirring rods, it was left in Erlenmeyer flasks, it was stuck in the funnel, it ran through the filter paper when it wasn't supposed to, it was stuck in beakers, it was spilled on tables, all over the place, unfortunately. What we really wanted was to get all of those atoms and all those molecules and all those formula units into the filter paper so that we could filter out the precipitate, collect that, and hopefully get 100% yield. Because of sources of error, because of contamination, because of reaction conditions, and for some fancier reactions, because of the type of reaction, we don't always necessarily have that reaction go to completion. Typically, we lose some of our product along the way, so what we call our actual yield is going to be less than our theoretical yield. All we do is compare those. We go to lab, we conduct the experiment, we measure our actual yield, our actual mass of substance produced, we compare that to the theoretical yield. Percent yield is really simple. Let me sneak this in here. Actual divided by theoretical. And it's a percent problem, so of course you know you're multiplying by 100. The amount that we really did get divided by the amount we should have if we did our balanced equation correctly in our mole tunnel problem, our mass calculation. And we hope that our percent yield is going to be pretty high. We're trying to get close to 100%, as close as we can. Certainly industry likes to do that. They're making things on a large scale. They're buying tons and tons of chemicals. They want to make sure that their reaction works well and they get as much product out as they possibly can, because that's how they're going to make some money. They also don't want to have a lot of contamination and waste because they have to dispose of all that. And if it's a hazardous substance, something maybe toxic or poisonous, there's plenty of rules and regulations on how those things can be disposed of, so they don't want to have to deal with all that. We want to run a good business. If we're going back to our brownie example, if we're making a recipe, say for chocolate chip cookies, we're not just taking out the bag of flour, dumping some in and saying, "Hey, that looks good," throwing in a couple blobs of Crisco and a few eggs and stirring it up and adding the rest of the ingredients and saying, "Yeah, those will be good cookies." We're actually measuring. We're taking careful measurements. That's what a recipe is. It's telling us exactly how much of each substance we need so that we get the best product, that we get the maximum yield. We don't want to have a recipe for chocolate chip cookies that has too much flour in it, because then they'll just crumble and fall apart and taste like nothing. We want everything in the right proportion so that the cookies are yummy and delicious. Who wants a cookie right now? Okay, so percent yield, pretty straightforward. That takes us to number 17, how to identify the limiting and excess reagents in a given reaction. And this question is about just a very general A and B react to make C and D kind of a question. The limiting reactant is the one that gets used up. So the one we're going to run out of first. An example you typically see in textbooks or we use in class in the chemistry department here is cooking hot dogs. Hot dogs happen to come in packages of 10. Buns tend to come in packages of 8. If we're trying to make hot dogs to serve at a party, then when we cook up our 10 hot dogs and start putting them in buns, we're going to run out of buns. The buns are our limiting reactant there because we can only make 8 hot dog sandwiches out of 8 buns and 10 hot dogs. We would have an excess of 2 hot dogs, unless it fell through in the grill. Number 18, what determines the limiting reaction, limiting reagent in a reaction